So as I mentioned before, part of this is about finding key lines, key points and so on. We looked at the chord. Let's have a look at tangents and normals. There's two approaches we could take. The first one, as you can see, is using parametric coordinates. The other way we'll end up looking at is using Cartesian. So let's have a look at some problems and some different things. So want to find the equation of the tangent. Remember, for the extension 1 stuff, it's always the standard one, where the vertex is 0, 0. We don't shift it. It's just x squared equals 4ay. So random point, we'll give it the parameter p, so its coordinates are 2ap, ap squared, and we want to find the equation of the tangent. So that's what we started using calculus for, you remember. If we differentiate it, the derivative will give us the slope of the point at any particular one. We just got to sub in the x value. So y is rearranging it, x squared on 4a. Differentiate that, we get x on 2a. Or another way I could have done it is I could have done it implicitly if you didn't want to make y the subject. And so I'd get 2x is equal to, and then on the right-hand side, well, I can't differentiate it with respect, so I'll differentiate it with respect to y, and I get 4a dy dx, and then rearranging that, you see we get the same thing. So probably most people just rearrange it this one. It's not too hard to make y the subject with this. So let's sub in 2ap. An interesting thing happens. Dy dx is equal to p. So what's that tell me? It tells me that the slope of the tangent is always going to be the same as the parameter. Whatever that number is that we sub in, that will be the slope at that particular point. Or I could have done it in parametric form. I could have said x is 2at, so differentiate that with respect to t, I get 2a. Y is at squared, differentiate that with respect to t, I get 2at. And so using our chain rule, dy dx is equal to dy to t times to t dx. And so I get 2at times 1 on 2a equals t. So again, we go, oh, look, it's the parameter. So it's a third way we could have come up with that idea. So when t equals p, there we go. Okay. Point formula. And I think I've put mine, there it is, as y equals. So y equals px minus ap squared turns out to be the equation of our tangent. Tangents from an external point. So here's a problem where I've got my parabola. This time I've set the focal length at 1 for this problem. So I've just got x squared equals 4y. I've got some point that's not on the parabola. So 3, 2 would not be on that parabola. Now from any external point, we should be able to draw two tangents. There's one of them. The question is, of course, what's the equation of the tangent? I don't actually know the point of contact. I don't know the equation of the tangent. That's what I'm trying to find. So it's not like I can solve these simultaneously and find the point of intersection because I don't know the equation of the tangent. So I'll just give that point of intersection a random parameter. Again, I'll just call it p. So in this case, because we know a is 1 for this question, that point of contact would be the point 2p, p squared. There would be another possible tangent that I could draw up the top there. And I'll just give it another parameter, q. So it would be the point 2q, q squared. All right. Well, I know y equals x squared on 4. Differentiate it, it's x on 2. So at my random points, which I don't actually know, I've just given it those coordinates. Then again, we notice, oh look, yeah, dy dx turns out to be p. It's the parameter at that point. And so for this one, I get, well, again, there's the equation of the tangent. The only difference here is a was equal to 1 for this problem. So I know that the line is y equals px minus p squared. That's great, but I don't know this parameter. However, I do know the line goes through the point 3, 2. So I could sub that in and work out the parameter. I can solve our quadratic and I get two possibilities. And so one is that it could be 1 and the other is 2. So q, I guess, would be the one where it's 2. So down here, p is when the parameter is 1. Up there, it's 2. So even though I don't know the point of contact, as long as I know one point that is on the tangent, I can still find that equation. And then all I've got to do is sub in p equals 1 and p equals 2, and I've got the equation of my two tangents there. Intersection. So where did two tangents meet? Another common question. So again, there's our standard one, gone back to the x squared equals 4ay, random points, there's a tangent. So the first thing I would do, again, is show, I'm not going to derive it again, we've already done it twice, but I'd go and show, okay, the tangent at P is px minus ap squared. And then there's another point. Now, when you're doing these sort of problems, you only ever derive these things once, because the only difference is the parameter. So if that's the tangent at P, then it's fair enough to say, well, the tangent at Q must be y equals qx minus aq squared. The only thing I'm changing is the parameter. Instead of P, I've got Q. Solve them simultaneously to find our point of intersection. So, all right, so I'll subtract to get rid of the y's. On the right-hand side, I've got difference of two squares, which will cancel with the P minus Q. And so the x value would be A times the sum of the parameters, P plus Q. And I can sub that back in for x to come up with my y, and y turns out to be A times the product of the two parameters, so APQ. So the point of intersection of two tangents will always be A, the sum of the two parameters, and then for the y value, A, the product of the two parameters. All right, let's have a look at the normal. And you'll remember a normal is the line that's perpendicular to the tangent at the point of contact. So something that looks like that. Okay. Again, I'm not going to do it again, but there it is. We know we can work out that the slope of the tangent is P. Well, if that's the slope of the tangent, then the slope of the normal must be minus 1 on P. And we can put that into our point slope formula. And rearranging that one, x plus py is equal to ap cubed plus 2ap. All right, is what we end up with. Intersection of normals, what does that look like? Is there a nice pattern to that one? So let's put in P, there's one normal. So we just found it was x plus py is ap cubed plus 2ap. That means my normal at Q must have the equation x plus qy is equal to aq cubed minus 2aq. Oh, I've written that down wrong, haven't I? So I'll find the point of intersection. Yes, they should both be plus. So to have that second one became minus there. Solve them simultaneously. And again, the p minus q is going to cancel, because p cubed minus q cubed I could rewrite as p minus q, p squared plus pq plus q squared. So p minus q cancels, and we get this interesting expression for the y value. Temptation is to factorise it, but it's not going to. So a outside of p squared plus pq plus q squared plus 2. And when we sub that back in to work out the x value ends up being minus apq p plus q. So a little bit more involved than the, there it is, look at that for a set of coordinates, eh? So the x value minus a product of the parameters times the sum of the parameters, that's for the x value, and the y value is just a wonderful expression there. P squared plus q, pq plus q squared plus 2. I suppose there's one reason why we don't try and memorise these. If we're going to derive them each time anyway, it's not that big a deal. But
so we'll have to derive it every time.
yeah, they'll usually get you to derive it. Sometimes they might give it to you if you're lucky.
So there's never any point in memorizing?
Look, you're going to start memorising them anyway, because you just do so many questions of them, it'll start sticking. That's going to be it. But yeah, no, there's no need to. Okay. Anyway, 9F, we'll have a go at some of those.